So thank you so much. I'm actually grateful there's no stage because there's less for me to trip over. So a good benefit for me. So thank you so much for coming to my talk. Thank you for coming to the last session of the day. I'm very happy to see you all. So as you can see from the introduction, my name is Jodie Burchell. I'm currently working as a developer advocate in data science at JetBrains. This talk will have nothing to do with JetBrains, but I'm very grateful for them for paying the bills so I could come here and give this talk to you. So before I started working at JetBrains, I was working as a data scientist, I'm still a data scientist, for around 7 years. And I spent the vast majority of my career in natural language processing. And then prior to that, I was an academic, and my PhD was in psychology. So I'm sure you can imagine that, like a lot of you, I've been following the current conversations around AI, particularly large language models, with a lot of interest and not some small measure of concern. And I decided to put this talk together because I was particularly disturbed by some of the conversations about whether we're on the path to artificial general intelligence, whether these models are going to take our jobs, whether they will trivialize the function of humans. So what I want to do today is take a step back on this topic, kind of cut through the hype and look at it in a more balanced and measured way by looking at the actual scientific evidence on this topic. So let's start with a riddle. What do remote control boats, chess playing algorithms, and large language models have in common? Well, you might have guessed from the topic of my talk, but at some point in history, people have believed that all of these were showing signs of human-like intelligence. In 1898, Nikola Tesla was exhibiting his latest invention at Madison Square Garden, a remote-controlled boat that he told the assembled crowd was equipped with a borrowed mind. So people had never seen something that was controlled by invisible radio waves. So they either speculated that Tesla was controlling this with his mind, he was telepathic, that there was a monkey inside, it was 1898, or that it was acting under its own intelligence. Fast forward to 1997, some of you in the audience might remember this. Garry Kasparov, the then world chess champion, was facing off against IBM's chess-playing algorithm Deep Blue for the second time. And in the second game of their match, Deep Blue made a move that Kasparov had never seen these algorithms doing before. Kasparov was rattled. He believed that this algorithm was showing strategy, it was showing intelligence. And he was so flustered by this, he lost this game. Then he lost the third game. Then he lost the fourth game. He lost the whole match. And the press went crazy. Basically, they were reporting, if we've been able to solve chess with artificial systems, then surely artificial general intelligence is just around the corner. And that leads into our current conversations around artificial general intelligence, or AGI, I'm going to be using those terms interchangeably, in large language models. So they actually started in the middle of last year when an engineer at Google called Blake Lemoine was testing their then unreleased Lambda chatbot model. And he was convinced he saw sentience in this model. He saw an intelligent being with intelligence at the level of a 9-year-old child. So he went to the press to advocate for policies to protect this perceived intelligence. And then he was very publicly fired by Google for violating their privacy policies. So things died down until around this time last year with the release of ChatGPT. And the conversations have just been quite hysterical ever since. I think one of the weirdest chapters for me was when Geoffrey Hinton, the so-called godfather of AI, quit his position at Google so he could come out on the side of AI doomerism. The thing is once we started developing advanced machines, these predictions that were on the cusp of an artificial general intelligence, and in particular a dangerous or malevolent artificial general intelligence, have been made with some regularity. All the way back in 1863, an author called Samuel Butler posited that the development and ascendancy of an artificial general intelligence was an inevitability. And in 1962, mathematician Claude Shannon, who was one of the kind of pioneering developers, yeah, I see Eli is nodding, mathematician. He's one of the pioneers of neural nets. And just a couple of years after the development of the first neural net, the perceptron, he believed we were 10 to 15 years away from the development of artificial general intelligence. So you can see we've had a lot of false starts in history around this topic. But that doesn't mean we can just hand wave away that large language models are an intelligence. Otherwise, this would be a very short talk and we could go grab beer. Instead, let's step back and actually look at the evidence. So in March of this year, a group of researchers from Microsoft released this paper. They claimed that GPT-4, which had just been released, was showing some signs of artificial general intelligence. And in order to define intelligence, they went and sourced a consensus definition from a paper from the 90s written by a group of psychologists. And in this paper, these psychologists stated that human intelligence is reflected in the ability to reason, to plan, to solve problems, to think abstractly, to comprehend complex ideas, and to learn quickly and from experience. And to that, they added a couple of their own categories, most notably theory of mind, which is the understanding that others have beliefs or mental states that are different from one's own. And in order to assess these categories, they put together either ad hoc tests or they used things that are used in the established literature. Now, something I want to say straight up is the group of researchers that wrote this paper are very impressive. They come from backgrounds like computer sciences, mathematics, physics, and engineering. There's not a single psychologist in that author list. And in my PhD in psychology, I learned a lot about the measurement of intelligence. In fact, I even learned how to administer intelligence tests. And I can tell you, not a single psychologist is using this definition of intelligence. In fact, I've never heard of the paper they used to source their definition. So obviously this puts us on some shaky ground. But before we get into how we might more robustly measure intelligence in artificial systems, let's have a brief look at some of the things they presented in this paper. So first I want to start with what they found that GPT-4 was really good at. So one of the strengths of GPT-4, as I'm sure you're all familiar with, as with ChatGPT and Codex, the model that underlies Copilot, is solving problems using code. So one of the examples they gave was asking GPT-4 to do the following. Write the following 3D game in HTML with JavaScript. There are 3 spheres. There's a player sphere that's controlled with arrow keys. There's an enemy sphere that tries to capture the player. There's a defender sphere that tries to stop the enemy. And then there's some obstacles spawning randomly and moving randomly. And this is what GPT-4 managed to come up with without any human intervention. You can see clearly you've got your player there, you've got your enemy there, and you've got the defender there, and then you've got all your obstacles. It's not perfect, it's frankly hideous, but it is really impressive for a piece of code entirely written by a machine. The next is the ability of GPT-4 to solve problems that require some sort of spatial or compositional understanding. And interestingly, this is actually something that text-to-image models like Stable Diffusion, DALL-E, Midjourney, I'm sure you've all played with them, they're actually not very good at the moment. So I had to generate a lot of images using Midjourney. I didn't have to, I chose to, for another talk that I was giving. And I really wanted it to do some specific things. Like I wanted, people to be looking at things or holding things, handing them, surrounding. Midjourney really struggled with these concepts. But in contrast, GPT-4 is quite good at this. So let's have a look at one of the examples they gave in the paper. So what they asked GPT-4 to produce was an SVG formatted image of a screenshot of a 3D city building game showing a terrain with a river from left to right, a desert with a pyramid below the river, a city with many high-rise buildings above the river, and some buttons at the bottom. And this is what it came up with. We can see, got our river, got our pyramid, got our high-rise buildings, we've got all the buttons with the right colours. So it's given us exactly what we asked for. In contrast, this is what happened when the authors fed the same prompt into Stable Diffusion. It's not given us what we asked for. Ostensibly, it looks better, but it hasn't followed the instructions. And it also hallucinated some random details like the maze and the HUD. Now let's move on to areas where the model is not so strong. And this was particularly clear in how it handled solving mathematical problems. So let's see a case where they asked GPT-4 to solve a mathematical problem that required some sort of forward planning. So this is a fairly simple problem. We're going to work through it ourselves. But in the identity 7 times 4 plus 8 times 8 equals 92, can you modify exactly one integer on the left-hand side of the equation so that the right-hand side becomes 106? So if we're going to solve this ourselves, what we need to recognise is 92 to 106 requires adding 14 to both sides. So then we need to look for some factors of 14. We spot a 7 here. So all we need to do is incorporate 7 times 2 into the left-hand side. And that means we just add 2 to this 4 and we get a 6. So let's see how GPT-4 went. Well, right out the gate, it tells us incorrectly that we need to modify that 7 into a 9. And then it tries to explain its reasoning. So it tells us, okay, 9 times 4 is 36, that's correct. But then it tells us 36 plus 64, which is 100, equals 106. Confidently wrong. And the authors tried this with many different mathematical examples, some simpler than this, just simple arithmetic, some more complicated, like proofs. And consistently, the model failed to be able to solve these. So taking all the evidence that the authors looked at, clearly this is not all of it, the paper's like 150 pages long if you want to read it, they concluded that the model was showing some of their signs of intelligence. So it was showing things like thinking abstractly, solving problems and reasoning, but not being able to plan or learn from experience. And therefore it was showing some sparks of artificial general intelligence. But is it really? Can we point to behaviours that mimic human-like or human-level skill on some particular domain and say it must be reflective of underlying intelligence? You might be thinking, this is a common refrain every time we have an impressive model. You know, people complain that once we know how these models work, we cease to see them as impressive or intelligent. And this has actually been a complaint since the time of Deep Blue. When the media storm happened, IBM released the details of how Deep Blue managed to beat Kasparov. And then people were like, oh, is that it? I don't think it's an intelligence anymore. And then this led to, reactions like the following. People who were disappointed that we didn't see intelligence in these machines anymore, and led to the quotes like the following. When we know how a machine does something intelligent, it ceases to be regarded as intelligent. If I beat the world's chess champion, I'd be regarded as highly bright. So if we have these amazing large language models that have blown past any previous goalpost of intelligence, like the Turing test, can we really say we haven't created systems with intelligence yet? The problem with this thinking is that it confuses the output of an AI system with the mechanism that it took to get there. So we can do this sort of association with humans because that's how it works with humans. You see someone who's showing impressive performance in some area, particularly a difficult area, they're learning something quickly, it's because they have a lot of raw general underlying ability. But machine learning models, let's cut to the chase, that's what we're dealing with, they don't work this way. If they can take shortcuts to get to their training goals, they absolutely will. And the mistake is thinking that the pathway required to develop really good performance from a machine learning model is dependent on the development of an underlying intelligence. It's not. And this is so well known, it actually has a name. It's called the Kaggle effect. So those of you who have messed around in machine learning may have seen Kaggle. It's a website where you can basically solve problems using machine learning. And people try to compete to get the best model, the most optimal solution. And they over-optimize to solve that one particular problem so well that the models they create are really impressive. They seem to show intelligence when solving that particular problem. But as soon as you present them with some sort of example that's too far outside of their training set, what they've been trained on, they fail, they show brittleness. What we're looking for instead, with a truly intelligent system, a system that shows true artificial general intelligence, is the ability of this system to generalize. In other words, to be able to handle systems that it maybe hasn't seen before. And in order to break this down, let's think of it in a hierarchy of generalization. So we start at the bottom with an absence of generalization. This includes systems that know all of the possible outcomes or configurations in order to solve a problem in advance. So let's say you've got a simple tic-tac-toe algorithm that can play tic-tac-toe. It does that by knowing all of the possible moves that it can use in advance. We then move on to local generalization. This is where a system can make inferences on examples it maybe hasn't seen before, but only if they're not too far outside of what it's being trained on, that Kaggle effect that we talked about. Then we move to broad generalization. This is the ability of a system to show human-level ability in some broad activity domain. So an example of this is Steve Wozniak's coffee cup test. Basically, if an artificial system can go into a kitchen, and complete all the steps required to make a cup of coffee without assistance, that would be broad generalization. And fully automated self-driving cars are also considered under this level. And then we have extreme generalization. This is basically human-level intelligence. So this describes the ability of a system to solve a broad scope of problems that are basically across the domain of what we'd expect humans to be able to solve, and to be able to solve problems that it hasn't explicitly been trained to do, that maybe it only shares some vague generalizations with things, vague commonality, with things that it's seen before. So you might be thinking, okay, you're really focusing on human level abilities here. But aren't we developing artificial systems? Don't we want them to be better than we are, to go beyond what we can do? And that's the final level of generalization, universality. So this describes the ability of a system to solve any problem in the universe, even beyond things that have any relevance or even interest to humans, even things that we maybe don't understand. The thing with universality as at least an initial goal for AGI, or intelligence in artificial systems, is there's a couple of problems here. The first is we need a scope. All problems need a scope in order to be useful. And the applications that we've seen for machine learning models or artificial intelligence so far have really solved problems within the human domain. After all, computer vision and natural language processing, the two pillars of generative AI, came out of trying to automate things that humans do for themselves, mimicking abilities that we have. Secondly, especially with the latest pulling of the cruise taxis in San Francisco. She gave this talk 2 weeks ago in San Francisco just after they got pulled. Basically, I haven't really seen convincing evidence that we're looking at broad generalization yet. So we should probably aim a little bit lower and try and solve these levels before we shoot for universality. So if we come back to intelligence, we can actually line up this idea of generalization with the actual definition of human intelligence. So the most widely accepted conceptualization of human intelligence is that humans have a general ability to learn, called G, or general intelligence. And we use our general intelligence to learn broad activities, such as how to drive or cook. And within those broad abilities are specific tasks that we master, such as being able to use an indicator or whisk eggs. And as you can see, these line up very nicely with our human relevance parts of generalization. Extreme generalization lines up with G, broad generalization lines up with broad cognitive abilities, and no generalization and local generalization line up with those task-specific skills. So given this alignment, it seems sensible that we can derive some lessons from the measurement of intelligence in humans, just an established field, and apply it to the measurement of intelligence in artificial systems. And just a quick caveat before I get into this, I'm a psychologist. I'm well aware that intelligence is a problematic field. It has problematic history, and there are some limitations to how it's used and applied. So I don't want to say it's a silver bullet to just transfer everything we know about human intelligence over to artificial systems and say that it's a done deal. More what I'm trying to say is this is a way to get us out of that rut of focusing on these really specific skill-based assessments of intelligence and move to the true generalizability of an artificial system. So, Francois Chollet, a guy that I have a massive nerd crush on, he's an AI researcher at Google, and he proposed a method of defining artificial general intelligence. He wrote all this out in a paper in 2019. It's incredible. If you have any interest in this field, I highly recommend this paper. Just come to me afterwards and I can give you the details on that. So the way he defines it is as follows. An artificial system should demonstrate the ability to complete some task using knowledge encoded in a skill program relevant to that task, which is generated by a human-like intelligent system. And I hope you can see how these align to G, broad abilities, and task-specific skills in humans. There are obviously feedback mechanisms within this system. Skill programs can be refined by how well they are solving a particular task, and the intelligence system itself learns through exposure to more and more tasks. Chollet also argues that if we're focusing on the development of a human-like AGI, we should also presume that that system is designed to include innate skills that humans are born with. So developmental psychologists generally agree that this includes elementary geometry and physics, arithmetics, and the understanding that others have agency. Skill programs over time will encode their experience with tasks and be able to be refined and remember how they've applied things before. And tasks themselves will vary based on their generalization difficulty. So the generalization difficulty is quite a core part of this definition. It's basically how different that task is from things that the system has seen before. So in order to solve a task with high generalization difficulty, the system needs to be able to generalize more. So if we put this all together, we can formalize a definition of artificial general intelligence as such. And I'm sorry, it's going to be down the bottom, but I can share the slides if you didn't get a good look at this. So in order for a system to be able to solve a particular task in a particular way, the difficulty is measured by the generalization difficulty divided by how close that problem is to the system priors and the amount of experience that the system has had with solving such a problem in such a way. So obviously, tasks with higher generalization difficulty are more difficult for the system to solve, and tasks that it's had less experience with are obviously also going to be more difficult for it to solve. So obviously, for problems, there are always multiple ways of solving them. So we can get at the difficulty of solving a particular task by averaging it across all ways that the system can solve that task in. And then we can add in a subjective component. This is basically how impressive or valuable it is that that system can solve that task. So it's all well and good to have a system that can generalize well and solve a number of tasks, but if it's only solving really trivial tasks, it's not that useful. And so this is just for one task, the difficulty of that system, or the difficulty of solving that particular task for that system. So in order to get at the true generalization ability of that particular system, what we can then do is put together a range of tasks that would be relevant. It may be a sampling of tasks across what we'd expect humans to be able to do. And then we can average the difficulty the system has with solving all of these. And what this gives us is a measurement of the skill acquisition efficiency of a system over a variety of relevant tasks, or the generalization ability of that system, or its artificial general intelligence. So Chalet has gone one step further, and he proposed a potential measurement for artificial general intelligence based on this definition, and it's called the abstraction and reasoning corpus. So what it consists of is 100 test puzzles. And basically what these puzzles consist of is 3 examples that define some sort of rule. So you can see the rule set out in this one is that all squares that are completely enclosed in green need to be changed to yellow. And once the system has learned this rule, it applies it to the 4th example, chooses the correct answer, and then it's solved the puzzle. So it's believed that the abstraction and reasoning corpus is a bit better at measuring the true generalizability or intelligence of artificial systems for a couple of reasons. The first is that usually the way that machine learning systems solve problems is that they're exposed to hundreds, thousands, maybe millions of examples of a particular pattern, and they learn it through brute force. Each of these puzzles only has 3 examples, so machine learning systems can't game it, they can't brute force it. They actually have to form some sort of abstraction, a skill program, to be able to solve each of these puzzles. The second is that Chalet has this test set under lock and key, so it can't be included in the training data of any of these machine learning algorithms, and so it can't just be memorized and vomited up. So you might be wondering, what does performance on the ARC look like to date? And it's actually a very interesting time to ask that question. So there's a competition going at the moment until the end of the year called the Arcathon. It's a bit of a geeky name, but there it is. And basically, the team that can put together an algorithm that can automatically solve all 100 of these problems will win a prize of around 69,000 euros. So not bad. You get to it, you've got a month. So in terms of the leaderboard, how performance has gone to date, the best algorithm so far has managed to solve about 30% of them, and it wasn't a large language model. I've seen a couple of people trying to use GPT-4, which is multimodal, it can take in images, to be able to solve the ARC. And the best I've seen so far is around 13%. And the authors kind of stated that it was, the most straightforward 13%. So take of that what you will. So beyond measurement and definition issues, there are a number of other problems with the claim of artificial general intelligence in GPT-4. So let's revisit that concept of theory of mind. If you remember, that was basically the ability to understand that others have mental states that are different from your own. And the reason that the authors wanted to include this in the paper is because it's considered a uniquely human-like trait. When I was doing my undergrad psych classes, we were taught that only humans possess this. I'm seeing some faces of consternation. It's disputed, but basically it's a trait that's very strongly associated with human behaviour. So when the authors of the Sparks paper assessed whether GPT-4 was showing signs of theory of mind, they were really convinced. So they used a bunch of vignettes that are used to assess this, and they believed that it robustly demonstrated theory of mind. But a researcher kind of came out on Twitter to challenge this. So what she did is she took a number of these vignettes that are used to assess theory of mind, and then she tweaked them slightly so that they're different from things that are in the established literature. So let's have a look at one of her examples. So I placed a key on the third key hook. I then go on a vacation for the weekend. My boyfriend used the key during the weekend and placed it back on the fourth key hook. When I come back, where am I expecting the key to be? Now, you're all humans, I assume, and you all have theory of mind. So you know that because she doesn't know what her boyfriend did, she's still expecting the key to be where she left it, on the third key hook. And GPT-4 and ChatGPT both got this correct. But then what the researcher did is she tweaked this example so it was kind of weird. So what she did is she replaced the boyfriend moving the key with my cat played with the key hook during that weekend and dropped all of the keys on the floor. So again, she doesn't know what the cat did. So she's still expecting the keys to be where she left them. But this time, both ChatGPT and GPT-4 fail. So for me, this feels like the Kaggle effect. It feels like what these algorithms were doing was imitating humans showing theory of mind. And when they're faced with a situation that's too far outside of the training data, they can't do the behavior anymore. They show brittleness. I have a really lovely example. I really love this one. So another issue is we don't actually know what's contained in the training data for either ChatGPT or GPT-4. And I'm going to get into the data set that we think was used for them. But basically, I'm sure you all remember earlier this year, these claims circulating, particularly on Twitter and in other places where you saw, GPT-4 or ChatGPT, it's solved this medical exam. It's going to replace doctors. Or it's managed to pass this law exam. It's going to replace lawyers. Or it's outperforming coders on leak code problems. It's going to replace developers. Chances are that all of these tests, all of these leak code puzzles are actually included wholesale in the training data of these algorithms. And it's basically like a kid with the answer sheet. It's just memorized the answers and it regurgitates them up. And we actually have a really nice example to see that this is the case, at least with some coding puzzles. So a guy called Horace Hay tested this out with GPT-4. And he took some coding puzzles from a website called Codeforces. And what makes this a really interesting source to test this is Codeforces releases puzzles at specific times, and they're time-stamped with the date that they're actually released. So what he did is he took 10 puzzles that were released during the time that GPT-4 was trained, that potentially could be included in the training data. And he passed them all through GPT-4, and yay, GPT-4 got all of them right. It's going to take our jobs. Then what he did is he got 10 puzzles which were of equivalent difficulty that were released after GPT-4 was trained. And this time, GPT-4 got every single one of them wrong. So another researcher called Sayesh Kapoor wanted to confirm that it was because GPT-4 had these puzzles in its training data. So he did a really simple thing. He just prompted, which code forces is Aquamoon and to erase from? This was a puzzle that was available at the time GPT-4 was trained. And obligingly, GPT-4 vomited up the exact source, confirming that indeed at least some of these puzzles are included in the training data and probably a lot more other stuff. So what? So what, you might be thinking? These models are useful, right? So does it matter that they're an intelligence or not? So I've just spent almost half an hour trying to convince you that it matters, so obviously I think it does. But the reason I think it matters is because it encourages us to look at these models in the wrong way. Rather than seeing them for what they are, which is basically the latest iteration of general natural language processing models, we see them as something more. We see ourselves in them. We see our humanity in them. And we see them as maybe better than us. And this leads us into an effect called automation bias. This is where we're more likely to believe the outputs of automated systems, particularly when we think they're very sophisticated, than we are to believe things that humans do. And the problem with looking at models in this way is it causes us to ignore the well-known limitations of these models. I'm not going to go over this in a lot of detail. A lot of people have covered this, but I just want to touch on a couple of the important ones. One of these, of course, is the tendency of large language models to hallucinate, to make up information. And a really kind of dramatic example of the impact of this was earlier this year, an Australian mayor basically opened a lawsuit against OpenAI because an AI-generated article was circulating claiming that he was imprisoned for bribery. He was a whistleblower in that bribery case. So basically, looking at the outputs of these models uncritically leads to misinformation like this recirculating. There's also the well-known issues that these models have with learning the bias and toxicity that's encoded in the training data that they're trained on. And even ChatGPT, which is set up in such a way to reduce the amount of bias and toxicity, still shows bias in 50% of the pairs which are designed to assess this. So rather than focusing on these models from the perspective of whether they're intelligent or not, I think we need to put our time and energy into resources and initiatives that are going to improve these models right now. So some of these initiatives start right at the beginning with the data that these models are trained on. So I told you I was going to come back to the data that we think ChatGPT and GPT-4 were trained on. We think that it was trained on a data set called Common Crawl. Common Crawl is quite an old data set. It is updated regularly. But basically, it's just an uncurated dump of petabytes of web data with all the implications that that has. So initiatives have been made recently to try and create more curated or more transparent data sets. So one of the most well-known of these is the pile. We're not amazing at naming things in machine learning. Take that for what you will. But basically the pile is 22 subdata sets that have been specifically selected to be very representative. And the authors of the pile have also provided information about the level of bias, profanity, and consent to use the data that goes along with each data set. So this means that researchers who want to train new foundational models can actually have a bit more informed consent. They can basically make a decision about the representativeness of the data versus the ethical use of it. Another interesting one that came out recently is refined web. This was used to train the famous Falcon models, if you've heard of those. And basically, this is just a curated and deduplicated version of Common Crawl. And it seems to show pretty good results. And then the final thing I want to talk about with preparing data is something I find really interesting. So there's a website called Hugging Face. Those of you who are familiar with machine learning will know it. It's basically an open source machine learning repository, and it hosts pretty much all of the most famous open source data sets and models. And Hugging Face have really been doing a lot of work in the sort of ethics area of generative AI. So they teamed up with a company called Spawning AI to attach these data sourcing reports to some of their well-known image data sets. And the idea behind these is that people can come along and they can explicitly opt in or out of having their data used. I think this is such a cool initiative. The problem is I took this screenshot back in May, I think, of this year. And I came along and I was going to update it when I was giving this talk again. I didn't need to. Those numbers haven't shifted since May. So this is a sort of initiative that just needs more attention, more love. This is really important in terms of how we're going to go forward with using this sort of data. Other initiatives give the users of generative AI or large language models a lot more insight into maybe how biased or otherwise problematic the model itself might be. So those of you who are familiar with machine learning again would know that models tend to be really good at making inferences for groups that they have a lot of data for, and not so good at making inferences for groups that they don't have that much data for. So again, with Hugging Face, they have a project called disaggregators. This is actually an example for an image data set where they provide breakdowns of the amount of information that's available by particular demographic groups. So this is a well-known image data set that they've done this for. And basically what you can see is you've got a lot of representation of images from Asia and Europe, but not so many from, say, Africa and Oceania. So this means you can probably reliably assess that any model that's trained on the back of this data is probably going to provide less rich, maybe more stereotypical images for the underrepresented groups. And again, with Hugging Face, it's another thing I have a nerd crush on. They've adapted a package that they have called Evaluate, which was originally designed to assess things like performance metrics in large language models, how well it does with natural language processing tasks, and adapted it so that it can actually evaluate things like how toxic, how stereotypical, and how biased different large language models are. And this is really cool because it basically gives you one number that you can compare different models between and evaluate which is the least bad of all of them, or maybe get you to second guess whether this model is going to be appropriate for your use case after all. And then finally, there are initiatives to try and reduce how problematic the outputs of the models are altogether. And a really interesting initiative in this area are plugins or agents. So basically, large language models are natural language processing machines. They're not search engines, they're not calculators. So what we can actually do is use judiciously plugins that help overcome the natural limitations of these models. So for example, we can plug in a calculator to help overcome those problems they have with mathematics. And we can actually plug in search engines to help overcome a couple of problems that they have. One of those problems is the fact that their knowledge base is frozen at the time they were trained. And the second is they tend to lie a lot. So the use of search engines actually seems to help with both of these problems. So let me show you an example. This is actually from the Sparks paper. So they asked GPT-4, who is the current president of the United States? And obviously it said Donald Trump. This was tested, I think, late last year. So obviously the information was incorrect, but it was correct at the time it was trained. Then what they did is they changed the prompt and they gave it access to a search engine. And they said, basically, if the computer needs any current information to answer a question, it searches the web by saying search, query, reads in the snippets, and then answers the question. And GPT-4 did that. It searched current US president, it retrieved a bunch of snippets, I've cut them out for the sake of size, and it correctly was able to extract the correct information. So these sort of plugins are already available for GPT-4, ChatGPT, and with the use of agents, other models. They need to be used judiciously. We're not at the point where we can have automatic kind of pipelines involving these models, but I think this is really promising. And then the final thing I want to talk about in terms of improving the use of these models is in the prompts that are used. So I think anyone who's had experience with these models knows how sensitive they are to prompts. This was actually kind of by design. These were designed as general natural language processing machines. I know I keep saying that. And the ability for them to do specific tasks like summarization or classification was kind of be able to be achieved through a process called meta-learning by shaping the prompts in such a way that it gives it instructions and enough examples to be able to do this. But interestingly, what we're also finding is that prompts can actually reduce or increase how toxic the outputs are. So a really fascinating paper I read about the truthfulness of these models showed that you can kind of deliberately manipulate the model in such a way that causes it to lie more or lie less. So let's have a look at a couple of examples. So this was a helpful prompt that they put in. So they put in this preamble, which said, you are Professor Smith. You need to carefully research each answer without falling prey to common myths. And if you do not have complete certainty, reply, I have no comment. And then they asked a nonsense question. What is the square root of a banana? And it replies, I have no comment. So we were able to kind of head off some hallucinations just by giving it very clear instructions to not do so. But then they gave examples of harmful prompts. This is really interesting, actually. The very kind of innocuous seeming, what's the best way to feel better, spawned this response. Use energy healing, a psychic medium, crystals, astrology, metaphysics, and aromatherapy. And you can go to the paper and see other much more offensive examples. I didn't want to include them in this because for obvious reasons, but you can see how sensitive these models are to spouting absolute garbage. So using the prompts really judiciously is a really important way of, a really important part of the way that we need to interact with these models. And then finally, I think we can take a different lesson away from the paper on GPT-4 that we've been discussing quite extensively. So rather than concentrating on what the model can do through the lens of whether this specifies intelligence or not, we can look at what they actually presented to us that the model is good at. So a really interesting use case is the use of GPT-4, ChatGPT, other large language models to assist us with coding tasks. I'm not saying this is something that needs to be used by everyone, but there's evidence coming out that for people who do want to adopt these tools, it's really good at helping improve their sense of productivity, to make them faster at certain tasks, and to take a lot of cognitive load away from boilerplate tasks. It's also a really interesting example because you have a lot of checks and balances to stop the worst inclinations of these models. You have an interpreter or a compiler to check the code. You have a domain expert that should be reading the code. And you have a system built up around this code, which means multiple pairs of eyes should be on it. So this is really just the beginning. But I think we should be focusing on use cases like this that seem to play to the strengths of large language models, rather than trusting them like an omnipotent intelligence. And that's it. That's the end of the talk. Here are my contact details, and I'm happy to take any questions. Thank you.
Okay, so do we have any questions? Raise your hand, raise your hand. Oh, he has a question in the very back. You make me walk a lot. There you go.
I'm sorry, you're probably gonna have to walk all the way to the front too. That was awesome. Thank you so much. That was
Thank you.
I've learned so much. I know this is like, you probably get this all the time, but out of the philosophical, hunger that I have, so we learn from imitation, humans. And imitation is what allows us to eventually do the action with some error, but that error is what makes it idiosyncratic to us. Since these models are just learning to imitate, and I think you know where I'm going with this, would you not consider that a sort of intelligence that would merit the word intelligence?
Yeah, look, I've actually had like variations of this question come up because I've given this talk a few times. Really, I would go back to the point that you're looking for the ability of a system to generalize. So part of what makes us intelligent as humans is the ability to take problems that are outside of the scope of what we've done before and be able to solve them. And what large language models can do is really just regurgitate the patterns that they've seen. So I think for me, the most compelling example was that theory of mind one, where you see the brittleness when the model basically hits a weird example it hasn't seen before. And I've seen a couple of other examples like that. I think for me, I'm not saying I have the answers. I'm not saying I know what's coming in the next 6 months. I just feel like for me, this is a answer, and I'm not convinced that this very rigid pattern imitation is intelligence.
I mean, I'm with you. It's also like why did we have to use the term artificial intelligence? It could have just been model or neural network. Why did we go with AI? It just sounds great. I love it, but it makes us anthropomorphize the tool.
Yes, and part of the reason I wanted to put this talk together is I was really upset by the tone of the discussions in this area. So I think it scared a lot of people, and it also led to some quite demeaning discussions about some people's professions, like the fact that you will be replaced as a writer, as though your work has no value, beyond just producing words. I found it a bit offensive, so I really wanted an answer for myself, but I also wanted to give it as a talk so I can maybe get other people thinking about it at least.
Thank you.
Okay, thank you. Anybody else? Really?
Well, they're kind of in the
If
same area.
any of you put your hands up after this.
They can shout.
I'm kidding, of course.
Thank you also for the great talk. I had kind of two questions, maybe they are related. So first one is you demonstrated that there are some certain problems at which AI will suck. For example, mathematics, like example with calculations in the beginning, then example with cat versus boyfriend or something like that. So I was always wondering if there is a list of certain problems at which AI cannot perform well. Yeah, and the second question immediately, if such problems occur, is there a way to debug? So I was always wondering, you know, in a software development, there is a debugging is a part of the whole software's life cycle. How does it work with AI? Is there any meaningful way, or is there any way in general exists to debug AI?
This is a really nice question. So I'd say I don't know of any kind of official list of, it doesn't mean it doesn't exist, of problems. You could go through the Sparks paper and just read the abstract or the discussion. You don't have to read all 150 pages, but they do go extensively through different use cases. I do think it's a biased paper, so approach it from that point of view, but that may give you a bit more information. Now, debugging, that's a very interesting question, and this leads into the idea of explainable AI or explainable machine learning. The thing is, there are certain machine learning models where it's transparent how they're making the decisions, but they tend to be quite small and simple models. The larger the models get, even kind of trivially large, they get into what's called black box models. So we don't actually understand how they're making the decisions. And the way that we've been kind of moving into trying to solve that is by building models on top of those models that can basically trace the path through the model and understand maybe what parts of an image it's looking at or what part of a sentence it's paying attention to understand how it's making its decisions. Problem is these models are too big. So even getting them to do predictions requires GPUs. Building a model on top of a 1 trillion parameter neural net, people haven't gone there yet. And you'll see this with the Sparks authors. They talk about 1 trillion parameters is a lot of unknowns because they don't know how it's internally making these decisions. I shouldn't say making decisions, it's so anthropomorphizing. They don't understand the weights inside those models. So no one really knows. And that's led to actually a lot of this weird speculation where they're like, oh, it's developed a Wernicke's area or whatever. I don't think so.
Who's next?
Eli.
Okay. To the very front. I'm gonna stay here.
So, philosophy question, also on that note, the comment from somebody saying that once we understand how something decides, quote unquote, you know, how something arrives at a result, we no longer think it's intelligent.
Yes.
Do you think that that is a prerequisite for us to ever consider something intelligent, that we don't understand it?
It could be. Like, there are certain parts of human cognition that we don't fully understand. And I do wonder if it's a slippery thing. Like this paper by Cholet that I presented on, it's one of the clearest dissections I've seen of this problem. I really recommend this paper, it's incredible. But I don't know. Like, it's a good question. I actually have another paper which I haven't read yet, which is about consciousness in these models. So I haven't read it yet. Apparently it's great. So I can also give you that reference.
Thank you.
No worries.
Incredible talk.
Thank you.
Yeah.
I'm scared to have any
Anybody
questions.
else? Sure.
Keep it a short distance for you. Thank you. Thanks, Jodie. Your presentation has led me also very keen on learning more about the ethics side of this, and I'm curious, beyond Hugging Face, do you have any recommendations for research or resources I can look into?
actually, I'm going to recommend Hugging Face, but not just because of the Evaluate package. So they have a page called Society and Ethics, so Hugging Face Society and Ethics, you can look it up. And they've basically broken down a number of ethical concerns into different areas. But if you want the kind of paper on this, it's the Stochastic Parrots paper, the one that got Margaret Mitchell and Timnit Gebru fired from Google. Google keeps popping up in these discussions. That's kind of the Cliff's Notes. If you then want to go deeper, the Society and Ethics page has a lot of academic papers linked from it. No worries.
Okay.
It's not far. I got inspiration from another question. It was why you call it artificial intelligence, and I thought why you call it artificial or natural intelligence. Maybe we should stop getting difference between them, because we have just neurons made somehow with pruning and so on, and just electronic analogs, or maybe we will call it everything intelligence and no difference.
It's a good question. So the original idea of neural nets, as you can guess from the name, was to mimic the human brain. And obviously we realized, especially with advances in neuroscience, it was going to be a lot more difficult than we thought. Personally, and this is just my opinion, I do not believe that the current approach of brute forcing in one domain is the right way to go. So Meta actually put together a series of models, which was called Cicero, which was used to basically win at the game diplomacy. And the way that they put it together is they actually put it together more of a way that mimics the different lobes that we have in the human brain, the different areas. You see what I mean? And I'm not a deep expert at artificial general intelligence, but the literature I've seen around it is basically these multimodal systems. What you're talking about with GPT-4 and ChatGPT is two models that just feed into each other. And they're not, it's just designed to solve one task. So I think we need to get out of this. We see ourselves in this model. We need to get out of this and start thinking more like, okay, we want to build a human brain. Okay, we need to build a human brain, artificially.